will have a third lecture now which is on dynamics of ocean structures. Let us quickly see what we have seen in the last lecture. We have discussed about fixed type platform, in that we have seen steel jacket platform, we have seen gravity based structure, we have seen jack up rigs. There is a specific name why we are giving this as jack up rig, because we are lifting the hull or the working hull and founding it in the soil using the steel lattice towers. We made a very brief summary of fixed type category of platform, saying when you design an offshore system, you focus on a different form which can cater for different kinds of sea states and water depths. If you look at the fixed type, it is one of the form which has a rigid base, it attracts more forces. The advantage is the response is less, depending upon the increase in water depth the system becomes expensive, and since the mass is very large in case of gravity based structure, it creates many problems like seabeds cover, interfere with the navigation, and cost of installation also grows expensive. We have also seen the common material which is being used for fixed type platforms. Most commonly you can use steel, people have used concrete and so on. Now, based on the material properties and the type of form, we derive basically three basic concepts of understanding required for dynamic analysis. One is mass of the platform. When we talk about rigidity, we talk about stiffness. When we talk about response, we talk about forces. When we talk about material, we talk about damping. We also talk about some of the non-linearities related to material and forces. So, these are all essential characteristics of a dynamic analysis. So, we understood from one type of platform that they are having very high mass, it is very rigid and therefore it is very stiff, and we are yet to speak about the environmental forces coming on the structural system. We will talk about that in the next lecture. We marginally touched about the damping characteristics which can be derived from the material, and we spoke about a very brief introduction of how do you get non-linearity. Now, interestingly, we summarized one important concept in the last lecture, that if you want to reduce the response for increasing in water depth, as well as I want to reduce the cost, I should not go for fixed type. Then I should go for a different form, a new form which has been evolved in the literature by the researchers is compliant type. Please focus on this spelling, compliant type. So, compliant means moving, compliancy stands for moving or movement. The moment I say movement, then I will speak about relative response. So, the net effective response in such structural systems will be greatly reduced. And interestingly, as an engineer you can easily understand, when I have a form which has movement, then I can say this form need to remain flexible. It means stiffness of these platforms are lower. The moment I say stiffness is lower or the system is flexible, it will attract less forces. Since the system is flexible, installation becomes complex. Why? Installation becomes complex. Why? Can you answer this? Why installation will become complex when the system is flexible? Imagine a floating ball or any floating body. The position fixity of the body in the large volume of water does not depend only on mass, but also depends on the buoyancy force which the fluid will exert on this body now. Whereas in the earlier form of fixed type, we did not have this problem during installation, but in compliant type, because of the flexibility introduced by you in the form, you have complexities in installation. So, how this complexity will govern dynamic analysis of such structures? To a very simple question, the answer is the governance of this complexity in dynamic analysis will focus on what is important now is free floating analysis, because while installation, due to the complexities introduced by the form, the structure may become dangerous in free floating state. So, you have to do dynamic analysis at free floating state as well as when it is being position fixed in your location of the sea state. So, now compliant form type of offshore structures are different in behavior in dynamic analysis with respect to a fixed type because of the following reasons. So, what are the different types of compliant platforms? Where are they constructed? What is the geometric shape? Importantly, when I say it attracts less forces, is it because the size is small? If you understand that the size of a flexible platform or the size of a compliant tower is smaller than that of a fixed type, then you are talking about the functionality of the platform. Remember, I am speaking about the form, not the function. So, the functionality what the fixed type platform had on the top side has got to remain same as that of a compliant type also, because if you say I want all those top side complications to be installed which has been already existing in a fixed type for exploratory and production drilling, I must have all those equipments, plants, machineries as same as that in a compliant type also, because any user will not compromise on the user oriented functionality of any platform because you want to make it flexible. So, the size more or less has got to remain same. I am not saying it has got to be exactly same, more or less it has got to remain same, but the weight has to come down because it has to remain flexible. Therefore, we can talk about hollow or void cylinders, what we call as pontoons. So, this is how this platform was evolved in geometrical design, that instead of having solid structures, go for void based elements, so that size can retain same, weight can come down. Because of the flotation characteristics, the structure can become flexible. The moment the structure becomes flexible, stiffness is reduced. The moment stiffness is reduced, it is tendency to have less number of forces coming on, attract less forces on the structural system. So, the aim, the focus on this design was, or on this form was, to reduce the forces. One may wonder, sir, when I have got material which can have yield strength as high as 1000 megapascal, when I have material whose yield strength can be as high as 1000 megapascal, why should I bother about a design which will attract less forces? Let us have the same problem, because I can design a member whose yield strength can be as high as this value available in the literature. Cross references, understand courses being taught on offshore structures and materials or design of offshore structures. There are material available referred by API where yield strength can be as high as this. Conventional steel will have an yield strength of around 450 to 550 megapascal, but you can have material of this strength also. Okay. When I have this material available, why should I focus on a design which will attract less force? Any answer?
Fatigue.
Sorry?
Fatigue.
No.
Cyclic rotation.
See, okay, we will just clarify what the gentleman said. He says fatigue is an important item where I am focusing, therefore I want to reduce forces. Remember, interestingly, fatigue is a problem associated to a force of lower magnitude, but in repeated number of cycles. I am talking about the cyclic loading. The magnitude is not a concern in fatigue loading at all. Okay. Therefore, I cannot speak about the magnitude of reduction which will result in fatigue. No, that may not be the right answer. Why I have to reduce the forces acting on the structural system? What should be the reason? Essential reason is, I want to take this platform at greater water depths. When I move towards greater water depths, the force exerted by the water body on the member will be increasing exponentially. So, I won't have a system which will attract less forces if I want to use the system at deeper waters. Now, the counter question is, why I cannot use a fixed type system at deeper waters? It is a very interesting reverse question. Answer is already available, what I said just now. I cannot use fixed type systems at deeper waters because fixed type system by its form have a tendency to attract more forces which I do not want to happen there. Now, the counter question is, if I have a member of very high yield strength, why I do not want to allow a member to have higher forces? Any answer for this? So, this will be a question for you for examination. Okay. So, remember this question. I have got 3 cross questions asked. The most important is, I have a material, but I do not want a form to attract more force. Why on design point of view? Why on material point of view? You have not answered. Okay. This is a question which is interesting for us. Let us move forward. Compliancy means movement. So, the tower moves. Okay. The term compliancy stands for moving. So, compliant offshore towers are actually offshore drilling platforms that are deployed in deep sea for oil exploration essentially, not for production. Okay. Remember, they are meant for exploration, but of course exceptions do exist. Not always that every platform is only for exploration, you can also use it for production as well. For example, TLP, okay, for example spar, but essentially they have been initially designed for exploratory drilling only. They are connected to the sea floor, but they are allowed to move freely, very interestingly. Now, the question is, how this is possible? I want to connect them to the sea floor, but I want them to move freely. I am connecting it to a sea floor, but I want them to move. Let us take a simple tower. I am having a simple tower which is a steel lattice tower which is cross braced. I am having a top side as you want, a multi tier top side, I am having all facilities like a crane, like a helipad, like a living quarters, all facilities, a drilling pool, etc. I want to found this or I want to fix this to the sea floor, this may sea floor. But I do not want to fix it thoroughly, I want to make it compliant. I have to make this joint essentially a hinged connection. There are varieties available in the literature for making it hinged. I will show you a video today. Very simple hinged connection being used by a person in a shop to put his banner on a road which is having enormous wind speed. I will show you that. Okay. So, hinged connection. The moment I say hinged connection, then how this can exercise flexibility or movement or compliancy. The hinged connection will give you the following facilities. One, it will make the system position restrained. It will make the system position restrained, but it will offer no restraint against what? Rotation. A typical classical model is hinged. Some people call this as pinned connection. So, interestingly, in mathematical modeling of dynamic analysis, modeling of joints play a very important role. In mathematical modeling, which is essentially required for dynamic analysis, modeling of joints play a very important role. Okay. So, once I introduce a hinged connection here, the system becomes flexible because it is now moving not in the position, but in rotation. So, interestingly, if you have a tower which moves, let us say, to this position hypothetically when the wave is acting. Now, there are two catch here. One, the deck should remain horizontal, because if deck gets inclined, then I cannot do my drilling operation. The deck should remain horizontal. So, it is essential that there should be a hinge required here also. Okay? We are not discussing that. The deck will remain horizontal, but when the tower inclines because of the wave action happening here, then if I have any mooring line, the mooring line will be exerted with some tension. The horizontal component of this tension will counteract the wave. Of course, the vertical component of the tension will add to the weight, which will improve stability of this platform under wave action. Okay. Now, what is the advantage of introducing a new member which will take care of the lateral force? Greatest advantage is my lateral forces do not come on this member, is it not? If it does not come on the member has got to be designed only for the forces generated by its own weight or by the top side. It means the member design becomes less complex. Therefore, I can go for yield strength of lower value and lower member cross sectional dimension. When I say lower member cross sectional dimension of decreased d, the Morrison forces coming on the system, which is a function of diameter, will be reduced. That is why I said these members will attract less forces. Okay. It becomes very easy for us to understand that I will introduce a member or set of members which will counteract my lateral forces, which will not allow the lateral force majority to transfer to the truss system. On the other hand, if you do not have this member and you do not have an hinged connection and fix it here, the whole lateral force has to be taken care of by this system only, which is a fixed type platform. Suppose you do not fix it here, hinge it here, but do not have a mooring line here, then there should be a mechanism by which the inclined position of the tower should be brought back to normalcy. To understand this, I will give you a very simple example of a toy which you have been playing in the childhood. You must have used this toy which is red in color. It does not have a tail, there are eyelashes to this, there are even ears to this. The toy has only a tip understanding here. The toy is a very simple basic toy which is being played by children. The interesting part of this toy is when you try to make this toy lie down, it does two things. Interestingly, which you have observed is the toy will close the eye, which you have seen. Which you have not seen is once you remove your hand, the toy will oscillate in position and come back to vertical. It is exactly the same model applied here, which is a spring mass system here, which integrates this weight and the shift of buoyancy or shift of weight to the spring action restores this position back. So, I have to have a mechanism here in such a way that I do not have an additional member like a mooring line, but I want to bring this tower back to normalcy without oscillation, but here the toy oscillates. Okay? I do not want that oscillation to happen. So, interestingly, if this is my still water level, I must have what I call a buoyancy chamber. So, variable buoyancy, which is an upward force, and the weight which is a downward force, because of the shift of buoyancy from here to here, it will offer a counterclockwise couple which will restore this platform back to vertical position. So, when you introduce flexibility because of joints, you must compensate this flexibility by some other mechanism like a buoyancy chamber, like a mooring line, etc. All these towers in general are called as compliant towers. Why compliancy was introduced? Because I want less force to be attracted on the member, because I want to use it for deeper waters. So, it actually depends on the stability. So, we have to bother about the stability part of it. So, stability becomes an inherent study in dynamics of floating systems. Stability becomes inherent study in dynamics of essentially floating system, but I will put it slightly as a compliant system also, because in my case the stability is important during installation. First, then of course during production or function. 2, 3, it should not collapse even at worst sea state. So, I must ensure safety. So, one important catch here is when you evolve a new form, people thought of different kinds of connections or joints initially. So, the form evolution started with introducing joints, which I call them technically as articulations. These are no more called as joints, they are called as articulations. Articulation is nothing but hinge or pinned connections as far as mathematical modeling is concerned. So, I am going to introduce joints. Now, you may wonder, sir, why joints are required only at the foundation part and only at the top side. Can I introduce joints or hinges somewhere in between? What would be the harm? What would be the difficulty if we introduce a hinge or a joint in between the length of the member? I can give an example for this. You must have seen at least movies of Bruce Lee. Bruce Lee used to use a specific chain which is nunchaku. It is having 3 connections, one rod, another hinge, another rod, another hinge and another rod. Even though these hinges give flexibility to fold this in any form he wants, but it requires a basic axial force to make this rod straight. Okay. So, multiple hinges introduced in any member needs basic minimum axial force to straighten this member or to remain this member straight. Another example is, you can see a game called pole vault. Pole vault is a game where people have a long and a high platform, there is a barrier here. The sportsman runs from here with a long stick in his hand, there is a pit available here. He comes and punches this tip in the pit here, jumps and falls. If you have seen this video any time during any Asian games etc., you will see as the man goes higher and higher, this pole vault becomes bending, keep on bending. So, there has to be a balance between the body weight of the sports person with respect to the self weight of the stick, which will enable him to push down on the other side. If I have a hinge anywhere in between, it will weaken the strength of this member. So, similarly here if you put hinges anywhere in between, if you have introduced hinges anywhere in between, it will weaken the strength of the member, but the member will become more and more flexible. If your focus is only to make it flexible, introduce the joints. If your focus is to make it restrained for loads, do not make it flexible as by putting a hinge in between. So, there are multi hinge towers also available, multi leg towers available and hinges only here available, hinges here and here available. So, structural form was evolved in such a way that people thought of introducing multiple joints and chambers and members to make it compliant. That was the whole idea, but this system has a demerit. I will come to that once we see some more slides here. Most interesting part is these structure avoid resonance because the operating frequency of this structural system are much well beyond the band frequency of waves. We will speak about this more in detail in the next coming lectures, but it is a very important hint. It is a derived advantage because system becomes flexible, the frequency range of operation shifts from the wave band. So, it is an advantage. Since we do not know any value about what is operational frequency, what is the frequency of the tower etc., we have not done any analysis yet, we will not speak about this insistingly, but it is a derived advantage. Okay. Say they provide lot of flexibility. As I said, the platform will remain horizontal, that is a flexibility given for exploration, not for design, okay, for exploration. I can make you to understand, if the platform does not remain horizontal, what would be the difficulty. All of you would have seen at least a circus in a childhood, okay, circus. So, in circus generally gymnastics people do, having a net at the bottom and they keep on doing the gymnastics at a very good height, maybe around 7 meters or 10 meters, maybe around 20-25 feet height, they will keep on doing gymnastics. At the end of the show, people used to fall on the net and they come down to the floor. Have you ever attempted to walk on a circus net? If you have a flexible base which is highly flexible, highly moving, you will not be able to walk on that. Okay. I will show you a very interesting video now. maybe after 2-3 slides, you will realize that how engineering introduction of these kind of joints has made innovations in different countries where people do not have understood engineering, but they have applied it. Okay, they have applied for a very interesting and simple example. So, introduction of any kind of joints or connections will improve flexibility, but reduces strength. Okay. As I said, these kinds of platforms are initially designed for exploratory drilling only, not for production drilling, but subsequently they have been extended for production drilling also. The original objective was only for exploratory drilling. I think we all agree and understand that what do you mean by exploratory drilling and what do you mean by production drilling. Before the drilling starts in a well in an offshore, people have to really find out whether there is enough potential yield in that well to invest on a platform for another 10 more years. So, we do first an exploration. So, that is what we call exploratory drilling. I need platform for that, I need a setup for that, may not be a platform, but I need at least a semi submerged or a drill ship which can drill at that particular location. This is what we call as exploratory drilling. Once the drilling yield value of the well is established, then one can construct the platform depending upon the revenue which we saw yesterday, one can invest and keep on earning money. And as you have seen, all of you will strongly agree that today the revenue of all the platforms in US and Gulf of Mexico has gone up at least by 55 paise. Okay, for 1 liter it has increased by 55 paise as on today. So, the revenue keeps on changing, right. So, offshore platforms, as long as they exist, there is no depletion value, there is only incremental value. Any other structure except monumental structure, they have depreciated value. Offshore platforms do not have depreciation, they have only incremental values. Okay, that is the only one interesting part what we have, which will encourage people to invest on offshore structural systems. So, we will quickly see a classical definition in the literature. What is about deep water? We are talking about the water depth, because that is one of the primary concern for us here. This definition is keeps on varying and is updated. You must have seen this definition in hydrodynamics classes, etc., but this definition is completely different. In 70s people said more than 80 meter was itself considered to be a deep water, whereas in early 90s people said up to 300 meter you can go, and beyond 300 is deep water. But in the recent past people said above 500 deep water, above 1500 ultra deep, above 2.5 kilometers it is super deep waters. Okay, there is a recent classification available in the literature. So, depth of water is classified depending upon these names with respect to the water depth available. So, my structural system should suit in the range between 500 to 2500 meters. The deepest platform now available is around 2220 meters. At this water depth it is operating. Okay, that is the deepest platform available now. So, one classified platform in compliant system is a guide tower. I think you have seen this figure which you have drawn, the line diagram I am showing here. These are mooring lines, there are different components of this. Deck is the top one, truss is the lattice truss what I showed here, and the cables what you see here are all mooring lines. For interesting information, I want you to remember these points. This point is technically called touchdown point. It is the point where the cable touches the sea floor, it is called touchdown point. This is the point where the cable touches the structure, this is called a fair lead. So, touchdown point is the point where the mooring line touches the sea floor, and the second point where the mooring line touches the structure is what we call a fair lead. Okay, fair lead. Now, interestingly, you cannot float a cable in water, yes, because the cable has no weight compared to the buoyancy offered by water. Cable will keep on floating, you will not be able to push and restrain the cable at any specific location you want. So, how do you do that? You attach weights to it, they are called as clump weights. You attach a weight to it and this weight will drag down the cable to the sea floor. Okay, they are called as clump weights, and once you put the weight, there is a possibility that because of seabed erosion the weights may get lifted up by buoyancy. To hold it down in position for permanently, use what we call drag anchors. We will talk about this slightly later. Drag anchors will hold it down, this cable in position. So, these are some of the minor components in dynamic analysis concerned, but these are very important for offshore platforms are concerned. So, we must have an idea about what we are talking about here. So, one derived advantage is that by using a mooring line or a cable, I am able to alleviate maximum component of the lateral load, preventing it from reaching my structural tower. My cable takes this load by an horizontal component of this. Is that clear? Any questions, any doubts here? This is what we call as a guide tower. It is not because it is a male tower or a female tower, or it is a neither male nor female tower as in US standards. The guy is because this is called as a guy line or a guy rope, that is the name given in the literature, that is why it is called as a guide tower. So, alternatively people thought that guide towers had some difficulties. Can you point out one major difficulty or deficiency a guide tower has? Major deficiency, structurally and functionally. Sorry, you have to be louder. Sorry, strain in the cable. Slender. No, we have not talked about any slenderness at all. Slenderness is okay. When you talk about stability, people confuse the slenderness. Slenderness is a proportionality between the cross sectional dimension and the boundary condition of the support. I have a same member very long and a boundary condition. The member may become slender. I use the same member but put intermediate connections, the member will no more become slender. So, slenderness is a concept, proportionality between the dimension to its supported or unsupported length. Let us not bother about that here. If you worry that my cable will be slender, cable has to remain slender. You cannot have a stiff cable, but that is not a structural demerit. I have a very serious structural demerit in this problem or in this form. What is the demerit? Very serious demerit. The demerit here is I am deliberately introducing a point of failure. I am introducing a point of failure. The point of failure obviously in the structural system will be the connection points of the cable. If the connection points of the cable fail, the structure will fail. So, you cannot always introduce a deliberate point of failure and say that is an effective system. Is it clear? The structure will adopt its point of failure automatically by the wave or by the action of environmental loads, that is inherent part of the structural system, but you cannot create a failure point and say beware about this point. That is a very dangerous design actually, okay. That is structural demerit of the system. What is the second problem? Okay, very interestingly, if the cable get pulled off either from the sea floor or from the fair lead, it gets disconnected from the tower. The moment the cable gets disconnected from the tower has no capability to restore its position under the lateral force, because the whole action in this problem is only from the tower, from the cable. If the cable does not exist, tower cannot come back to its normalcy, tower will fall. Okay, that is a different story. You are going on to the next slide, but I am looking for the second demerit of this system itself. It interferes with the navigation. The problem is all these platforms require drilling vessels or tugboats or any offloading facility to reach my platform. My platform cannot be accessible closer because these mooring lines will disturb my navigation. Okay? So, interference with navigation. And is there any other problem? Any other serious problem introduced? Somebody said few minutes back about this issue, I counteracted that issue. Can you come back to the same issue back again? Fatigue. Think about the mooring line tension forces. Will it remain constant all the time? No, it will keep on changing. So, any increase or decrease in axial tension is a reversal of cycle of forces, right. So, mooring lines will be subjected to extraordinary fatigue stresses, and that is dangerous, okay. Fatigue in mooring lines. I am writing short forms here. MR does not stand for Mr. mooring line. It is also Mr. because we are talking about guide towers. Now, interestingly, as one gentleman said, forget about the mooring lines, can I have a buoyancy chamber? That is what we say in articulate towers. The next type of platform is a tower with articulation, nothing but a deliberately introduced hinge or a pin at a desired location. It can be anywhere you want. Mondays can be at the bottom, Tuesdays can be at the top also, okay, anywhere you want. It is a form designed by engineers. So, these towers are meant for small fields, shallow waters. Essentially the buoyant chambers are used for storing crude oil. Now, you have a buoyancy chamber here. This buoyancy chamber depends upon, depending upon its location and size, keeps on giving extra force in the upward direction, which will cause a couple. I have a buoyancy chamber here, for example, the buoyancy force acting at this location, self weight is also acting here, exactly collinear, perfectly stable, no problem. When my buoyancy chamber tilts, there is a shift of buoyancy respect to the center of gravity, and that will give me a couple which will restore the platform to normalcy, okay. Now, think of having a buoyancy chamber at the bottom here. Now, it is here. If I put it here, what would be the disadvantage, or is it an advantage? A buoyancy is associated with variable submergence. There has got to be a level of variation in submergence. If you put it here, it is completely submerged. There is no possibility of this variation happening. Where is the buoyancy going to vary? It will not happen. What is the second demerit? One is functional demerit, second operational demerit. Buoyancy chambers, yeah, sorry, there is a possibility of getting punctured, okay, but they are concrete chambers. The operational demerit is these chambers actually used for storing crude oil, right. Interestingly, imagine in 500 meters you are pumping the crude oil up to the platform and store it back below 500, what happens to the pressure loss, okay, it is lost, right. So, try to keep it as close as to the mean sea level. In this figure, why the buoyancy chamber is bigger than the ballast chamber? I want a very simple one word answer for this. Why the buoyancy chamber is bigger than the ballast chamber? Is it wrong? Simple one word answer. You have only 5 minutes time, so I want to show you a very small video, which I promised I have to do that. Very interestingly, I want the buoyancy force greater than my ballast force, because my cycle should be anti-clockwise for a lateral load, number 1. Number 2, buoyancy force depends on not on the size but on the submerged volume. So, as large it is, as high it will be. Thirdly, I have got large container to store crude oil, which is one of the important requirement for such platforms, if it is used for production. Yes, people use iron ore, not necessarily water, people use iron ore. Is that clear? Now, I have a very interesting question for you which you will answer. Why the ballast chamber is located at the bottom and the buoyancy chamber at the top? Can it be reversed? I need not want the answer now, think about it. So, I will close it here now, but I want to show you a video which is very interesting. I want you to think about this video, how the design was done. So, look at this board, I have deliberately taken it horizontal. So, no foundation, it is resting on the floor as it is. So, look at the connection at the bottom, it is subject to very high wind pressure. See the flexibility the board has, and the joint what you have is not a ball joint, it is a simple spring mass damper system, and see the flexibility. Equivalent natural example of this is a palm tree on the beach side. Okay. So, look at the joint, this is what we are saying, position restrained but not restrained against rotation. If you do not have any questions, we will close. Okay.